So this situation we're going to start next is actually unique to at least 3 or more variables. We can't do it with only 2 because there's sort of not enough variables to do it. So we'll do it only for 3 variables in this class, but you could, if you really wanted to, do this for 4, 5, and so on variables as well. And what we're going to do in this case is we're again trying to extremize f is f of x, y, z subject to some constraints. Right? So extremize this subject to. This time, though, we want not 1 constraint, but 2. Right? So subject to g of x, y, z equals c and h of x, y, z equals k. Okay? So c and k, of course, are constants here. So what we want to figure out is how can we do this extremization problem? How do we figure out what the Lagrange multipliers look like? So what we're doing, in some sense, so the equivalent problem, so we can also think of this as we are trying to extremize right? Because if we're going to subject it to both of those equations, it's kind of subjecting it to the place where those 2 equations meet, which is a curve. All right. So we still want that, or we still know that the gradient of f is perpendicular to this curve of intersection. All right, which is good. But what we don't know is the gradient of f perpendicular to either of these surfaces? And usually the answer is, in fact, no, it isn't. So in that situation, then how do the Lagrange multipliers work out? What we do know is, since the gradient of f, right, so gradient of f is perpendicular to this curve, okay? And then we know another thing. And think back to the video on finding the tangent line to the curve of intersection of 2 surfaces. We know that the gradient of both g and h are also perpendicular to this curve of intersection. Because remember, that curve of intersection lies in both surfaces, so therefore it has to be perpendicular to both gradients, right? So, or also, I guess I want to say here, also, grad g and grad h are perpendicular. Actually, I forgot to say, gradient of f is perpendicular to the curve, but only at a particular place, at the extremum, or extrema, right, at any of them. Okay? So, how does this help us? Well, since one of the directions of the curve, there's 3 directions in space. One of the directions is taken up by the tangent vector. All right? So no part of gradient f can be in the direction of the tangent vector. All right. So what does that leave you? What are the other 2 directions? The other 2 directions must be these 2 gradients, the gradient of g and the gradient of h. So what does that mean? That means that the gradient of f at p, at an extremum, has to be a combination of these 2. So lambda gradient g at p, plus we need another Lagrange multiplier, let's call this one mu, gradient of h at p. Okay? So that's what it means, right? So again, I'll just recap that really quickly. Since the gradient can't have any components that are tangent to the curve, it must be made up of the other two directions in the three-dimensional space. But those other two directions are formed by the gradient of one surface and the gradient of the other, right? Because these two surfaces can't be sort of the same. Well, if the two gradients are parallel, then actually these two, don't really give us any information there. Okay? So we have that condition. And then that's our new Lagrange multiplier condition. So the Lagrange multiplier system of equations are now given by gradient of f equals lambda gradient g plus mu gradient h, g equals c, h equals k. Right? So this is the system of equations to solve in the case when we have two constraints. Right? And I'm not going to write this down, but you can imagine if we had, say, 4 variables, we could do 3 constraints, and it would look very similar. Just add on and multiply a multiple of the gradient of the new constraint, and then pop the new constraint down there. And that's all there is to it. All right, so see you in the next video for an example of this.